Today we're going to be talking about 2.7 Vesper and bond hybridization. This is just the first part, just an introduction. Our topic is based on the relationship between Lewis diagrams, Vesper theory, bond orders, and bond polarities, explain structural and electron properties of molecules, and the skills argumentation, supporting a claim with evidence from representations or models at the particulate level. What determines the shape of a molecule? Well, we know that negative electrons repel each other due to Coulombic forces. Bonds and lone pairs of electrons, which we call electron domains, are negative in nature, and bonds and lone pairs of electrons will arrange themselves in order to minimize repulsion. So, for example, we would never see carbon tetrachloride, carbon tetrahydride, or methane, CH4, looking like this. All of the, and I apologize for the handwriting, all of the hydrogens would never occupy the same side of the molecule. Why? Because these bonds represent electrons, and electrons repel each other. So they want to spread apart as far as possible. So our key point is that Vesper theory uses the Coulombic repulsion between electrons as a basis for predicting the arrangement of electron pairs around a central atom. Vesper stands for valence shell electron pair repulsion theory. Again, it just means that the valence shell electron, those outer electrons, are repelling each other. And electrons repel each other and will be as far apart from each other as possible in a molecule. So notice our methane, carbon tetrahydride, is right down here with a bond angle of 109.5, and those hydrogens are as far apart as possible. This is called a wedge, this black triangle, and that means that that hydrogen is pointing out of the computer, and this is called a dash, and that means that hydrogen is pointing into the computer. So between all of these hydrogens is a bond angle of 109.5. They are spread apart as far as possible. Now notice, with ammonia, NH3, we have 3 hydrogens and 1 lone pair, and the bond angle has decreased slightly to 107. With water, H2O, we now have 2 lone pairs of electrons, and the bond angle has decreased slightly to 104.5. So the question is, what is more repulsive, a bond or a lone pair of electrons? Hopefully you realize that lone pairs of electrons are more repulsive than bonding pairs of electrons, which can be seen because when methane has no lone pairs of electrons and it has a larger bond angle, these bonds are able to get further apart than oxygen, which means that these lone pairs of electrons are taking up more space than the bonds. They're more repulsive. They need to be spread apart even further, and they need their own space even more than a bond. And that's because in a bond, the electrons only can occupy a certain space. Lone pairs of electrons have more freedom to move around, so they occupy a larger space and fully belong to only one atom instead of being spread apart in a bond. So I would recommend pausing the video, taking a picture of these molecular structures on this slide and the next slide. This is a really, really great reference. It shows the electron groups on the central atom. So how many groups, so this could be lone pairs or bonds, does the central atom have? So in a linear atom, this central atom only has 2 electron domains. The number of bonding atoms could be 2. These 2 blue balls are bonding atoms. The number of lone pairs of electrons is 0. It only has 2 domains, and both of those are bonding. The AXE stands for A is the central atom, and X is the bonding atoms. E is lone pairs of electrons. So the chemical formula, well, we would just have 1 central atom and 2 bonding atoms, and this shape is molecular, and the bond angle is 180 degrees. An example of this is carbon dioxide, where we just have 2 bonding domains on that central atom. Even though there's 4 bonds, because they are double bonds, they just occupy 2 sides of carbon, so it's 2 domains. And although there are lone pairs on the bonding atoms, on the oxygens, there are no lone pairs on the carbon Trigonal planar has 3 electron groups. So you can see it's going to have it could have 3 bonding atoms and 0 lone pairs, or it could have 2 bonding atoms and 1 lone pair. If it has 3 bonding atoms and 0 lone pairs, then it is trigonal planar with an angle of 120. And if it has 2 bonding atoms and 1 lone pair, then it's bent with an angle of less than 120 because that lone pair of electrons is taking up more space, so it pushes that bond angle to make it smaller. A tetrahedral shape has 4 electron domains, 4 electron groups, so it could have 4 bonding atoms and 0 lone pairs of electrons. It could have 3 bonding atoms and 1 lone pair of electrons, or it could have 2 bonding atoms and 2 lone pairs of electrons. And all 3 of these would be considered, the electron geometry is tetrahedral. Each of these central atoms has 4 electron domains, and if it has just 4 bonding atoms, like methane, CH4, that's called a tetrahedral molecular geometry as well. If it's ammonia with 3 bonding atoms and 1 lone pair of electrons, it's trigonal planar. And if it's water with 2 bonding atoms and 2 lone pairs of electrons, it would be called bent. And so notice both trigonal pyramidal and bent have an angle of less than 109.5, and tetrahedral has a bond angle of 109.5. So here are a few more. Take a minute to study them. And during class, we'll be playing around with some of these structures and really seeing how to form them and why they form that way. So let's check for understanding. 2 possible Lewis diagrams are shown below for cyanic acid. Diagram 1 and diagram 2. Experimentally determined information about cyanic acid is presented below. So notice that shape of the molecule. Choose which diagram best agrees with the experimental data presented and justify your answer using Vesper theory. Feel free to refer back to those charts on the previous 2 pages and try and figure this one out.